So quantum distributed computing may refer to many things. It may refer to protocols to transmit quantum information through a quantum network. But here we will consider quantum distributed computing as a study of quantum protocols for solving classical computational problems. So problems with classical input and classical output. And for classical computational problems, quantum distributed computing have mostly been studied in the framework of two-party communication complexity. Indeed, there are very few results focusing on more than two parties, and even fewer results focusing on problems directly relevant to people doing distributed computing. So one thing that you can do on anonymous networks, you can design exact quantum algorithm for electing a leader. It's known that it is impossible to do this classically unless you are using random bits. But on non-anonymous networks, on the other hand, there are only two works that focused on distributed computing, and all these works reported essentially negative results. So they showed the impossibility of having quantum distributed computing faster than classical distributed computing for many important problems, like the computation of the shortest paths or the computation of the minimum spanning trees. So the question is, at least on non-anonymous networks, can quantum distributed computing be useful? In this work, we say yes. We show that with quantum communication, we can compute the diameter of the network faster than the best classical algorithms. Okay, so what is the diameter? The diameter is a fundamental parameter of graphs. So in this work, all the graphs will be undirected and unweighted. So the diameter of a graph is simply the maximum distance between two nodes. So for this graph, for example, the diameter is 4 because the most remote two nodes are node G and then node F, and their distance is 4 ops. So another fundamental quantity is the eccentricity. So the eccentricity of a node U is defined as a maximum distance between U and another vertex of the graph. Okay, so for example, the eccentricity of A is 3 because the most remote vertices are F and G at distance 3 from A. And of course, you can define the diameter as the maximum eccentricity. And we will use this characterization later in the talk. Okay, so now let me explain the model. First, the model of classical distributed computing. So there are many models in classical distributed computing. So we will consider one of the most basic models called the congest model. In technical terms, this corresponds to the study of non-faulty, non-anonymous, and synchronous distributed computing with limited bandwidth. So what does it mean? So we have a network represented by a graph of n nodes. So in this talk, n will always denote the number of nodes. So the nodes of the graph represent processors, and the age of the graph represent communication channels. Okay? And we assume that all the nodes have distinct IDs. So for example, here we have 6 distinct IDs, 1, 2, 3, 4, 5, 6. And we now assume that each node initially knows only the IDs of its neighbors, and also the total number of nodes of the graph. So for example, node 4 only knows that it is connected to 1, 3, and 6. It does not know anything more about the global topology of the network except the total number of nodes. And we assume that communication is synchronous between adjacency nodes. So communication arrives round by round, and at each round you can send one small message through each edge. Okay? Small message, what's the meaning of this? So there are several conventions. We will use the most standard one. That is, we assume that you can send one message of size at most log n bits. Why log n? Because log n is exactly what you need in order to send one ID. Okay? So at each round, you can send one message in each direction of each edge, a short message, at most log n bits. Of course, all the message may be distinct. There is no need to have the same contents in each message. And then, after the first round, all the nodes can perform some local computation. And then there is a second round where everybody again sent a short message. And then local computation. And then again a communication round. Okay? So the complexity of a protocol is defined as the number of rounds used by the protocol. This is the main difference with communication complexity. In communication complexity, we are mostly interested in the total number of bits exchanged. Here, we are not interested in the total number of bits, but in the total number of rounds needed for the computation. Okay, so now I will give you one instance of typical instance of computation that you can do on a network. The computation of the distance. It's a very fundamental computational problem. So suppose that node number 6 wants to compute its distance from node 1. Of course, the answer is 2. Okay, but how to compute this? There is a very simple algorithm that does this. It's called the breadth-first search algorithm. Okay, and it will compute all the distance from node 1. Okay, so the node 1, so the source, will send first a message to all its neighbors. Okay, so now at the end of round 1, each node will update its distance. More precisely, each node that received the message at round 1 will set distance equal 1, because they know that their distance from the source is 1, because they received the message at the first round. So distance equal 1, distance equal 1, distance equal 1. And now, round 2. The nodes tell new knowledge to the neighbors. Okay? So all the nodes that updated their distance at round 1 send a message to their neighbors. Okay? And then at the end of round 2, each node updates its distance. So for example, this node received a message from node 2 at the second round, so it knows that its distance is 2. The same here. And this one received a message indeed from node 3, but it does not make any updates because it already knows that the distance is 1. Okay, so you repeat this, and how many times do you need to repeat? The number of rounds needed is exactly the eccentricity of the node 1. Okay, so remember the definition here of the eccentricity. Okay, so now this protocol, this very important algorithm, the breadth-first search algorithm, can be used to compute for any fixed node U the eccentricity of U. How to do this? You apply this algorithm, starting with U and not 1, and then all the nodes will know their distance from U, and then you need to compute the maximum distance. So you take the maximum of all these numbers. And you can do it simply by centralizing the information at what node and taking the maximum. So this can be done in big O of D rounds. Okay, so this is easy to compute the eccentricity when the diameter is small. But computing the diameter, so it's easy to compute, the eccentricity when the diameter is small. But computing the diameter, that is the maximum eccentricity, it's much harder. It's known that this requires n rounds, even for networks with small diameter. So more precisely, we can show that distinguishing between a network of diameter 2 and a network of diameter 3 requires n rounds. Okay? So it's a very hard problem. And in this work, we show that we can do better in the quantum setting. Okay, so what is a quantum setting? In short, it's very simple. Now, quantum bits can be sent instead of bits. So the message is simply quantum. It's the only difference. And we don't even need to consider any prior entanglement. So formally, it's exactly the same as before, but now the processors need to be quantum processor because we need to process quantum information. And the only difference now is that the message consists of log n qubits instead of log n bits. Otherwise, it's exactly as before. Okay, so our main result is this upper bound. We show that there is a quantum algorithm that works in big O square root n d rounds and computes the diameter of the network. Here, n is the number of nodes, and d is the diameter. Okay? So remember that I mentioned that we have the lower bound of n rounds classically, and this lower bound holds even for networks with constant diameter. This means that whenever the diameter is smaller than n, you get a speed up. And the speed up is up to quadratic. It's quadratic when the diameter is constant. Okay? And this is the first gap between classical and quantum in the Conges model for a major problem of interest to the distributed computing community. So I wrote in here for a problem of interest to the distributed computing community because any separation between classical and quantum in the two-party communication complexity setting can be seen as a separation in the Conges model. Okay? So it's not the first separation, but that kind of separation are not very interesting. Okay. So this is for the upper bound. We also have lower bound. So we have a first lower bound, which is unconditional. It's square root n plus d. So it is tight when d is small, for example, when d is constant. Okay? But it's not tight when d is large. And we have a second lower bound, which matches the upper bound, but it is conditional. More precisely, we are able to prove this lower bound only for quantum distributed algorithms that use a small amount of memory, polylog qubits of memory per node. And actually, our algorithm, our upper bound, use an algorithm with this amount of memory per node. So we can say that our result completely characterize the complexity, the round complexity of quantum algorithms with small memory computing the diameter. Okay, and we also have some results for approximating the diameter, but I will come back to this at the very end of this talk. And I will start discussing the upper bound. Okay. So let's consider the decision version of the computation of the diameter. So I give you an integer d, small d, and I ask you to decide if the diameter is larger than d. Of course, if you can solve this decision version, you can solve the original version by using binary search. So now, observe that deciding if the diameter is larger than d means deciding whether there exists a vertex with eccentricity larger than d, because the diameter is the maximum eccentricity. Okay, so this is essentially a search problem, and we can try to use Grover search. Okay, very simple idea. So let's write it as usual for Grover search. You define this function f on the set of vertices. So fu is equal to 1 if and only if the eccentricity of u is larger than d. And then what we want to do, we want to find a vertex u such that fu is equal to 1, or report that no such vertex exists. And we know how to do this using Grover search. Okay, Grover search tells us that there is an algorithm, a quantum algorithm, that solves this problem with square root n calls to a black box evaluating the function f. And n here is the number of nodes of the network. Okay? So now let's recap a few details about Grover search. So Grover search, as you all know, repeat square root n times this operator, the Grover operator, and at the end do a measurement. And we can show that the result of the measurement is a solution with high probability. So what is this Grover operator? The Grover operator consists of applying the oracle, then applying Hadamard transform, the phase operation, and the Hadamard transform. So the point here is that the only part that depends on f is the oracle. Okay? The other part does not depend on f. Okay? And f here is a function that evaluates if the eccentricity is larger than d. So f depends on the network. So this oracle depends on the network, and this part does not depend on the network. So now our idea will be to compute the diameter by implementing this circuit. Okay? So we will choose one arbitrary node of the network. We'll call this node the leader. Okay? Any node can be a leader. We choose an arbitrary node. And we will ask the leader to implement all this circuit. Of course, the leader can implement this part locally without any communication. This part locally and this part locally. But the leader cannot implement this part, the oracle, locally, because the oracle depends on the network. So anytime he will need to implement a call to the oracle, he will need to communicate with the other nodes. So the total number of rounds of communication of the simulation will be equal to square root n, the number of times the oracle is called, times the number of rounds needed to implement the oracle. Okay? So the only thing that you need to understand is the number of rounds needed to implement the oracle in a distributed setting. Okay? And we will show that you can do it in a big OD rounds. Okay? So remember, we want to implement the oracle that compute f. F essentially computes the eccentricity. So we want to compute, to implement this oracle. Of course, the quantum oracle, so we want to be able to call it on superposition. Okay, so when the input is this, we want the output to be this. And I will explain how to implement it on one example. This example with 7 nodes. And we assume that the leader is this node. That is A, which is the leader, and A will try to implement this oracle. Okay, so A wants to implement the oracle. This means A has as input this state here and need to compute this state. Okay, so it needs to implement to apply the oracle on his input. And the first step is to broadcast this state in order to get this state. So what does it mean? The node A will first introduce a new register here, 0. And it will apply a CNOT to obtain a U here. And then it will send the second register to node C. Okay, so the register C here will be a register owned by the node C. And C will do something similar. It will introduce 3 registers, okay, initialized to 0, and apply CNOTs, so that now you have U appearing here. And will send the 3 register to the nodes on the bottom here, B, E, and D. And we continue like this. And at the end, you will get this state, where each of the 7 registers is owned by one of the 7 nodes of the graph. Okay? So I explained how to do this broadcast operation on this simple example. In general, you can do it on an arbitrary graph using essentially the same algorithm as I explained in the first part of the lecture, the breadth first search algorithm that propagates the information from the source. And the cost, the number of rounds needed to do this is exactly the eccentricity of A. Okay? So this is the first step. So now, second step, all the nodes implement the classical protocol for computing the eccentricity of U, which put the value, the output, the eccentricity, in a new register here. So we assume that this new register is owned by A. So A has 2 registers, this one and this one. And then last step, the node revert step 1. Okay? So this will remove all the intermediate register, B, C, D, E, F, G, okay, up to all these things. So we obtain exactly this, what we wanted. So the only slightly subtle point is step 2. Okay, in step 2, we are using the contents, the value of U, to control what the nodes are doing. Okay, so all the nodes share the same U, so they are all executing the same global algorithm that compute the eccentricity of U. So what we are doing, we are executing a quantum superposition of execution of a classical algorithm. And the fact that we are working on a quantum superposition does not lead to any interference or to any further congestion, because we are working in the computational basis. Okay, so the conclusion is that you can implement one call to the oracle in D round, so you get this complexity. Okay, so to summarize everything here, the approach is to elect a leader. Any node will be, it's okay for a leader, and you ask the leader to implement the Grover search. And the leader can do everything locally except the call to the oracle. And to implement the call to the oracle, you need to communicate. Okay? But you can implement it essentially using the classical algorithm that computes the eccentricity in D rounds. Of course, you need a quantum version of it, as explained in the previous slides. So this gives you the complexity square root n, the number of iterations, times d, the number of rounds to implement one call to the oracle. And with further work, the complexity can be reduced to square root nd. So how to do this? Here I said that in D round, classically, I can compute one eccentricity. It's a very simple algorithm. But there is a much more clever algorithm, fairly recent algorithm, that says that in D round, you can compute simultaneously the eccentricity of D vertices. So now the idea will be to divide the set of vertices into groups of size D. So you will have n over D groups. And you will do a Grover search over these groups. So the number of iterations will be square root n over D. And for checking, you will need at each step to check whether one group contains a vertex with large eccentricity. And you can use directly this algorithm, or quantum version of it, to do it in D rounds. So the overall complexity is square root n over D times D, which gives you square root nd, which is exactly the bound I claimed here. Okay? So the only thing I didn't explain is how to do it with a small number of memory. This is fairly technical, so I won't give details of that. Okay, so now lower bounds. So all the lower bounds here are actually obtained via two-party communication complexity of the disjointness function. It's a very standard technique to get lower bounds in distributed computing. So the first one, the classical lower bound. It's obtained by reducing the disjointness function to the distributed computation of the diameter. You show that if you have an efficient distributed algorithm for computing the diameter, you can convert it into an efficient protocol, two-party protocol, for computing the disjointness function. And we know that this function is hard in the communication complexity setting. So this implies this lower bound on the round complexity. Okay? Or conditional quantum and unconditional quantum lower bound, the square root n here. It's obtained using exactly the same framework. But now we use the quantum lower bound on the two-party communication complexity of disjointness function, which is square root n. Instead of n, you have square root n. So that's why we get a square root n here. And the d here is trivial, because d is always a lower bound. Because if you have less than d round, you cannot propagate information through all the network. So now, the conditional lower bounds. It is one of the most technical parts of the paper. The idea is to show the following claim, to show that if the quantum distributed algorithm for the diameter use few quantum memory, a small amount of quantum memory per node, then this reduction can be adjusted to give a two-party protocol for the disjointness function that uses few messages. The idea is to send communication in batches. But the point is that we will also need to send the contents of the memory of the nodes of the network. So we can do it efficiently only if the nodes use few quantum memory. So it's the reason why we have the condition here. And then we use a recent, very nice lower bound on the communication complexity of the disjointness function. So it has been presented in QIP a few years ago. It's a very nice result that says that any quantum protocol for the disjointness function that uses only R messages require n over R qubits. Okay? So if R is small, the bound is very close to n, which is much better than the generic bound here. So by combining these two things, we are able to prove the square root ND lower bound. Okay? So now summary. So in this work, we have been able to show that it's possible to obtain sublinear round quantum computation of diameter in the congest model. Okay, when the diameter is small enough. And we also have lower bounds, okay, which are matching if you assume this condition. And of course, the open problem is to prove an unconditional lower bound, matching lower bound. That is to prove that all lower bound holds even for quantum algorithm using an arbitrary amount of memory. So I believe that it is true, but I don't know how to prove it. So now a few research directions. So first, all upper bound is obtained by showing how to implement quantum search in a distributed setting. And more generally, our papers give a generic framework for distributed quantum optimization. So how to maximize a function or minimize a function. It can be seen as generalization of quantum search. So it's a very general technique. So it should be possible to use it to speed up many classical distributed algorithms. So the first research direction will be to find such kind of applications of this technique. The second direction is approximation algorithms. In practice, we are often okay with a good approximation of the diameter. Okay? And in our paper, we gave some result. We show this upper bound on the quantum round complexity of approximating the diameter with approximation factor 3/2. The point is that when d is small, this gives a speed up with respect to classical algorithms. But when d is large, this gives a worst bound. So this upper bound is not really tight when d is large. So it should be possible to improve it. So it's an interesting research direction. And the last one would be to prove a superiority of quantum distributed computing for other models. So in this work, we considered the congest model, which is one of the most important models in distributed computing. But there are other models. And in particular, there is a very important model, which is a local model. In the local model, the difference is that we have unlimited bandwidth. So we don't have any restriction on the length of the message sent per round. So you can send arbitrarily long message per round. And recently we have been able to show that in this model there exists a task that can be solved quantumly using a constant number of rounds, but classically requires a linear amount of rounds. So there is a huge gap here in that local model. But of course, there are other models. You can consider non-synchronous models, faulty models, and many other things. So it would be, I think, very interesting to go through all the models studied in the classical distributed computing literature and to try to see if there can be a speed up if you allow quantum communication. Okay, thank you. Yes, actually this one can actually be implemented with a very small bandwidth. So this, yes, this is an example of, yeah.
So it seems that if there's even one faulty node, then this algorithm wouldn't work, if I understand correctly.
Sorry, I didn't understand.
So it seems that if there's even one faulty node, then the algorithm wouldn't.
Yes. If it is faulty, it doesn't seem to work. Yeah. So right. It's not clear what we should do.
Yeah. So have you considered sort of algorithms in this for computing the diameter with sort of faulty.
Yes,
or
it's
small number of faulty
very
nodes?
difficult. So you have to define what faulty means. But if there is one node that goes completely that cannot be used in the protocol, it's not clear at all what you can do. Yeah, yes, you're right. Yeah. Okay. Yeah.
Hey, you mentioned dividing the Grover search over groups of size D, but if you're trying to find D, how do you do that?
Yeah, so the point, it's a very good question. So of course we don't know D, but it's always very easy to compute an approximation of D. Okay? So you know that you take any node, you compute the eccentricity, which can be done efficiently, and twice the eccentricity is always an upper bound on D. And the eccentricity is a lower bound on D. So you have a good approximation. So it's enough for making the division and the partition.
When you try to estimate. My question is about computing the eccentricity in parallel between all of them. Doesn't that create a problem with the bandwidth?
No, because it's not in parallel. It is in superposition. So it's a delicate point. Yeah, it's a subtlety. Yeah, it's a superposition. So you are fixing U, and when U is fixed, it's only you are computing one eccentricity. So it's not parallel. So it's a subtlety. You're right.
So your algorithm sort of requires coherence over the whole of the network.
Yes.
Do you have a feeling about what the situation is if you only allow kind of local coherence?
I don't know. No, all we have done here, it's really using an ideal model of quantum computation with everything is okay. So it's really the next thing is considering errors and faults in the process. But I don't really know what can happen here.
Thanks for all the questions. Let's thank Francois again.